Hey, geometry. This is round 2 of proofs, section 2.5. They've got a couple more postulates for us. One of them we're going to write down, the other one, we're going to go through but not really talk about too much. And then we got to actually do kind of a full proof. I felt like in section 2.4 we kind of got some easy ones thrown at us. But example 1 takes a little bit more work to fiddle through. And then we've got, a kind of a more realistic example for example 2. So this first postulate that we have is, I don't know why they even put this in there. It's kind of silly. It says the points on any line or line segment can be put in a one-to-one correspondent with real numbers. Okay, that sounds like a whole lot of jumbo. What it basically says is that if I have a segment AB, this line right here, I can measure it with a ruler. That's terribly exciting. Let's go down to the next one. This one is one that we're going to write down. Segment addition postulate. He has a name other than postulate 2.9. He is segment addition postulate. And this basically says that if I have a segment ABC here, ABC, okay? B is not necessarily in the middle, so we don't know that B is the midpoint. But what we do know is that if we know the length of AB and we add that to the length of BC, it makes the entire length of AC, okay? If you think about this with numbers, if this is 13 and this is 5, then the entire thing is 18, okay? So it says AB plus BC equals AC, and that's what the segment addition postulate says, okay? So we are going to come over here and we're going to write that down. Is it a postulate? Postulate 2.9 is the segment addition postulate. Okay, I'm going to draw out my diagram over here. ABC, I'm going to make it kind of evident that B is not exactly in the middle, and I'm just going to say AB plus BC is equal to AC. That's the segment addition postulate. Okay, we'll use him for quite a few proofs going forward. Okay, let's bump back to section 2.5. Here is where we're going to use that segment addition postulate. So prove that if CE is congruent to FE, CE is this chunk, if that's the same length as that chunk, and ED, which is this chunk right here, is the same length as this chunk, then we're going to say that this guy is the same length as this guy. Okay, the two small pieces are the same, the two larger pieces are the same, so the entire length is the same as the other entire length. Okay, that should be true, right? So let's write out our given and what we're trying to prove. Given CE is congruent to FE and ED is congruent to EG. Then we're trying to prove that CD is congruent to FG. All right, so given, oh shoot, we got to write that down here again. Given, sorry, we're going to do a lot of rewriting here. CE is congruent to FE. ED is congruent to EG. Okay. Okay, so again, this is kind of the smaller pieces. I'm just going to make notes off to the side. These are the smaller pieces. These are the larger pieces. So the smaller two pieces are the same and the larger two pieces are the same. So this guy's the same as that one. This one's the same as that one. So we're trying to prove that the entire lengths are the same. So let's talk about those two smaller pieces added together. Okay, so let's talk about CE and ED. We know from the segment addition postulate that what is it? CD, the entire length, CD is made up of, let me go around the other direction. Let's go, CD is made up of CE plus ED. Okay, that's the segment addition postulate. The smaller piece plus the larger piece makes up the entire piece. Okay, now on that same note, if I talk about the other side, like this segment right here, we can say that FE plus EG is equal to FG. Okay, the two smaller pieces added together make up the entire length. And those are both the segment addition postulate. Okay, now we know from this given statement that CE and FE are the same thing. So these two things are the same thing. So what I'm going to do is, since CE and FE are the same, I'm going to take CE and I'm going to plug CE in for the FE that exists right here, right? So this top row, I'm going to leave him the same. CE plus ED is equal to CD. I did not change him at all. But this FE that's down here, since FE is the same thing as CE, I'm going to plop CE in for that, okay? Now, in the same way, this is true. ED and EG are the same. So what I can do is I can take ED and I can plop him in wherever I see an EG, like here. I can take this guy and I can replace him with an ED. Okay, so let's rewind. What I did, let me see if I can erase this. EG. Okay, I took this guy and I replaced him with CE because that's what he is. I took EG and I replaced him with an ED because that's what he says up here that they are equal to. Okay, our very first statement. So I have CE right here. I have CE plus ED equals CD, and CE plus ED equals FG. Okay, that was all from substitution. I substituted these guys in here at the top for their respective values down below. And the last thing I can do is say, okay, well, if CD plus ED equals CD and CE plus ED equals FG, then CD is equal to FG, right? I can take CD and I can plop him in for this chunk here because that's what he's equal to. He's equal to that. Okay, so I can take CD and I can plop him in there. So CD and FG are the same, and that is from another substitution. Okay, and that's what we were trying to prove, was that CD is congruent to FG. I should put my proper notation. CD and FG are the same. By substitution, that is true. So that was a little bit harder to get through. Yeah, if you struggle with that substitution, you can log on to my office hours and I can kind of talk through that with you, okay? We wrote these down in the last section that we talked about, the reflexive, symmetric, and transitive property. I'm not going to write them down again because we've already written them once, but the transitive property, let's go through that one more time. Basically says if AB is the same length as CD and CD is the same length as EF, then AB is the same length as EF. So if we know that AB is 5 and CD is 5, right? Those two are the same length. And CD is 5, but then EF is also 5. These two are the same length, okay? Well, then I know that AB is obviously the same length as EF, okay? Those two match each other. So that's just kind of illustrating the transitive property as well. So kind of going through the reflexive, symmetric, transitive property, we might use those again down here. So, down here, the route for a charity fitness run is shown. Checkpoints X and Z are the midpoints between the starting line and checkpoint Y and the finish line. Okay, so this is the start. This is the end or finish. And then this is kind of like the middle between the two, but it's not a midpoint technically because it doesn't go in a straight line. So this is kind of the midway stopping point. And then it says X is the midpoint of this segment here, and Z is the midpoint of this segment here. Okay. That doesn't say given, but that is kind of what we're given. So I'm going to say X is midpoint of SY, and Z is midpoint of YF. Okay, that's kind of what we're given by these statements up here. Okay, prove that the route from checkpoint Z to the finish line is congruent to the route from the starting line to checkpoint X. So checkpoint Z to the finish line. Z to the finish line would be ZF. We're trying to prove that ZF is congruent to the starting line to checkpoint X. Okay, so that's congruent from S to X. Okay. All right, so let's start with our given. X is midpoint of SY, and Z is midpoint of YF. That's given again. We end up writing that like a whole bunch of times if you haven't figured that out already. Is this our last proof? Yeah, perfect. All right, so X is the midpoint of SY, Z is the midpoint of YF. Now, using this information, where can we go from there? Okay, well, what we can do is, using that information, if X is the midpoint, I'm going to erase some of this stuff over here so we can kind of see this. If X is the midpoint, if this is exactly in the middle, what that tells me is that ZX is the same length as XY. Excuse me, SX, not ZX. SX is congruent to XY, okay? And also, if Z is the midpoint, then YZ is the same length as ZF. Those lengths are the same. So YZ is congruent to ZF, okay? All right. Now, oh shoot, we forgot one more piece of given information. That's okay, we'll get back to it. So how do I know that this is true? How do I know that these two things are true? That is because of the midpoint theorem. We wrote that down on our theorem sheet the last time. These guys told me that they were the midpoint, so then I can draw this conclusion from it, okay? There's one more piece of given information that we forgot to write down that's really important. It says, if Y is the same distance from checkpoints X and Z, I'm going to put that over here. Y is congruent, or Y is the same distance from checkpoint X and checkpoint Z. Y, okay, so Y is the same as to checkpoint X as checkpoint Z. That is kind of like saying that XY, the distance from X to Y, is congruent from the distance from Y to Z. This distance here is the same as this distance here. So they said it in words, but we're going to write it in symbols. XY is congruent to YZ. Okay, so if XY is congruent to YZ, we've got to write that down here. And what can I put on this line? I can put given. Usually we list all of our given information as our first step, but you don't necessarily always have to, okay? So now we're starting kind of with this information, and we're trying to see where does this given information fit into play in that, okay? Well, I know that YZ, I know that YZ is the same thing as XY. XY and YZ are the same thing. So basically, if this is XY up here, I can plop YZ in its spot, okay? So SX, instead of it being congruent to XY, I can put a YZ in that spot because that's what he's equal to. That's what this piece of information says. And I can do that by using substitution, okay? And then I'm going to take this step right here, since those were kind of at the same level, and I'm going to rewrite him, but I'm not going to change him. So I really just took this first line here and replaced the XY with the YZ, okay? Substitution, that's what I did there, all right? Now let's read what this says. If SX is the same thing as YZ, and YZ is the same thing as as ZF, then what conclusion can I draw there? This is kind of like saying A is equal to B and B is equal to C. So I can say A is equal to C. So I can say that SX is congruent to ZF. ZF is congruent to SX. Ooh, we're kind of close. That was by the transitive property. Okay, now we want exactly ZF is congruent to SX, but we have SX is congruent to ZF. So what allows me to flip that around? That's true, but what allows me to flip that around is the symmetric property. Right? That was the property that kind of said that if 2 equals x, then x equals 2. That's that symmetric property. Okay, so there he is. That was a little bit more in depth. I hope you guys made sense of that. Proofs are awful things. They're tricky and they're hard to understand, and especially with this being your first exposure to proofs, I am so sorry that I'm having to do this not in person with you, because these are kind of tough. Okay, so hopefully you guys can make it through that. Yeah,